Now we're going to have a look at online methods. So this is going to be, if you've seen, for instance, the Walpole Rabbit talk today, going to be fairly familiar. But in general, well, here's the type of problem that you want to solve. So let's just go back to a simple binary classification problem. I mean, this is basically how it all starts, and it's the first instance of a stochastic gradient descent algorithm. And these algorithms are very powerful, and you can actually prove very nice regret bounds on it. I'm not going to go and prove a lot of them. I'll just show you, based on the Perceptron, how this can actually be done. I'm going to show you expected regret bounds, or expected loss bounds for the general convex stochastic gradient descent. But I'm not going to show you adversarial regret bounds in general. Not that the proof would be a lot more complicated, it's just that, you know, at some point I think we've done enough proofs and should probably move on to the algorithms and apply them. So let's say we have ham and spam, and then, you know, you could really find any such classifier and it would, you know, do the job perfect. And intuitively you would think that if, you know, those two sets are really far apart from each other, the problem's really easy. And if they're really close to each other, the problem is really hard. And that's the intuition that we're going to exploit when we then want to solve the actual estimation problem. And the Perceptron is an algorithm which started with, for instance, you could trace it back to Hebb's rule. In other words, you know, positive reinforcement, negative, you know, punishment. You know, you can learn a linear separator accordingly. So the algorithm is in itself strikingly simple. You know, you start with your weight vector being 0 and, you know, 0 offset. And then you just compute whether you got things right. So if a new xi comes along, you compute, you know, your linear function as you would. You check whether you're on the right side of the hyperplane. If you're not, so if this is less equal than 0, then update w with, you know, yi times xi. And update b with b plus yi. So in other words, in the end, you're going to actually end up with a linear combination of those xi's and w. And you're going to end up, you know, with, you know, some integer which tells you how many times you've seen a 1 versus a minus 1. You keep on doing that until, well, you're through the data set and everything is classified perfectly. Now, if you get things right, nothing really happens because then the constraint is not triggered, and so in the end you get a nice solution for the weight vectors. So, you know, you get f of x is, you know, sum over xi, so there's a yi missing here, plus b. Okay, so correct the yi here and out. And actually the realization that you can do that and you can also kernelize that maybe about a decade ago would have given you a cold paper. So it's a paper at a very good conference. And so the cool thing is, there exists some w, if there exists some w star b star with unit length, and for which I can separate things with a large margin, so a margin larger than rho. In other words, w dot x plus b times yi have to be greater than this rho for both sides. Then the problem is easy. So this rho directly measures how easy the problem is by telling me that if my data is contained in a ball of radius r, then that's the maximum number of steps that I need to take in order to converge. That's basically the size of the ball that contains the data. That's essentially 1. I mean, okay, this b star, you can make it go away, but yeah. But it's basically the radius that contains the data divided by the width of the space that we have to separate the positives and negatives from each other. If you think about it, that actually makes a lot of sense. Because if I have a ball, and I can squish the positive and negative classes out to, you know, just the poles. So if my positive and negative instances are just here and nowhere else, then pretty much anything that I pick will separate. Whereas if my data is all scattered around here, and maybe then the negative guys are all scattered around here, then it'll take me a fairly long time to find, you know, some hyperplane that I can thread through here and that actually separates the two half spaces. And the perceptron convergence theorem tells me that not only is it the case that, you know, intuitively this problem is a lot harder than when everything is just at the extremes, but it also tells me that there is a nice polynomial time algorithm for that. The other cool thing is it's independent of the dimensionality. It doesn't depend on the order in which I see the instances. So this is a very highly desirable algorithm in a way. Now let's just prove it. And the proof is very simple. So the first thing that you need to do is you need to show that your parameter vector becomes increasingly aligned with the true, you know, with that large margin separator. So we just compute this alignment, wi dot b with w star and b star. Okay, so at step j plus 1, we can expand it in terms of j, and then our update. Because if we didn't update, well, everything would have been the same anyway. So now we know that this term here, okay, so just writing out things a little bit further, this thing here has to be properly separable by the data. Right? Because that's exactly my condition on W star and B star that I have. So I'm basically expressing the new alignment in terms of the old alignment and how well the data can be separated. I know that this has to be separable by at least rho, and then by induction, so therefore I can show that this is actually, well, j plus 1 times rho. So, small typo here. So, no, sorry, no, it's actually j, so we initialize w1 and b1 to be 0. But basically what I know is that my alignment with a proper solution increases at least linearly in the number of errors. That's good. Now, of course, that doesn't mean that the vectors are actually becoming more collinear. It just means that the inner product increases. To show that they are actually becoming very much collinear, I need to have an upper bound on the amount by which the length of the vector increases. So what I want to be able to do is I want to have a slow rate for the length, namely actually in this case square root number of updates. And I want to have a linear lower bound, which is what I already got myself here, in terms of alignment. And then of course in this case, you know that at some point you have to stop. Okay, so the next step requires such exotic things like Cauchy-Schwarz. So, well, let's just, you know, take that inner product. That's of course upper bounded by, you know, the length of that, of the true, you know, optimal separator, and then, you know, the length of my parameter vector at a given time. And now I'm going to upper bound this. So that term squared, just by, you know, binomial formula expansion, gives me these terms. So it gives me the original vector length squared plus this term here, which I know had to be negative because I, after all, screwed up at this instance, right? So this can't go away. And I know what the length of this is. The length of this is exactly radius plus 1. Radius squared plus 1. So therefore, I know that the square length of the vector increases also linearly. Now, so what I therefore have is a lower bound for each iteration, and I have an upper bound for the alignment. The only way to satisfy this, if I plug this in here, is by satisfying this inequality. And the largest j that satisfies this is exactly the upper bound on the update counter. Because after that point, it's impossible for me to make yet another update. It's a not super intuitive proof in the sense that you're trying to prove well, conversions of an algorithm, and instead of that, you're basically proving an upper and a lower bound on some properties of your parameters and making sure that at some point this set has no other solution. But it's actually, you know, it's the first convergence proof of this type of problems, and it was vastly influential. Now, before I carry on, quick question: who has played black and white? Okay, only one. Okay, so maybe the game's been around, it's too old. But I think you had a question.
So what's Lstar? Why is it one?
So
The first, second one.
okay, so in this line, this is really just expanding the, you know, that sum.
No, I meant step 2.
Step 2. Okay, well, that's Cauchy-Schwarz. So A dot B is less equal than the norm of A times the norm of B. And now what I'm doing is I'm just plugging in what I know about the norm of W star and B star. Because I require that this is less equal than 1 and this is, you know, B star squared, so I can explicitly compute it.
Also, it's still less.
Yeah. And yeah, that should be another. Well, no, actually, there is an equality. Well, I'm assuming that this is of length 1. So that's an equality here. Now, okay.
The second line of step 3.
Second line of step 3.
From second to third.
Well, okay, so what we did here is we just expand. That's completely innocuous.
Yeah.
Okay, this term we recognize. This one, the same. Now this term here we make go away, but that is the case because we know that we update it at an error. So we know that this inner product has to be less than 1, or less than 0. And so if I throw it out, I can only make this an inequality. Right? So this can only get looser, so therefore I can throw it away. That's why we have a less equal. And then we just upper bound it further again. Yep.
Quick question. So at each time when we update our W, so is it, so why don't we take like a larger or smaller step? So just multiple.
Okay. Extremely good question. Why aren't we taking different step sizes depending on how things go? Well, as a matter of fact, this is pretty much what we're going to do later on for general purpose stochastic gradient descent algorithms. It just turns out that for the perceptron it's sufficient to update with 1s and -1s. But in general, you're absolutely right, you should be doing something a lot smarter than just 1s and -1s. Okay. Now, the cool thing is, you only really need to store errors, right? So this gives us a really nice compression bound. Because you can essentially show, well, you can show that you could throw out everything from the data except just the errors. And it basically means that we're actually doing stochastic gradient descent, which I'm going to explain in a moment, or hingeless. Now, a big warning. This thing goes badly wrong if the data is not separable. And this is my favorite warning example. So, okay, so at some point, well, it's like only one more guy in the room played black and white. I don't know whether you played version 2 or version 1. I played version 1, so. And what became very clear very quickly, I mean, it's a very ingenious game where you have an avatar that learns from your behavior and you interact with the avatar, and through that you basically make the avatar do what you would want to do. And the avatar can be, you know, one of those beasts. Now, basically you're playing God, so that's why it's a nice game, right? Now, unfortunately, what happens is that after a while, this avatar becomes extremely difficult to control. The game becomes very frustrating at that point. Basically, it stops being fun. And so I first didn't understand what was going on until I read an article by the guy who actually developed the, quote, learning algorithm for black and white, and showcased it as such a big success story for the use of perceptrons and machine learning in, well, computer games. Just turns out that this was an extremely stupid idea, because basically what happened is the avatar or the game assumed that the user would be, or the player would be, perfectly consistent and the type of feedback that it would give to its avatar. And perfectly consistent within the set of features that the game designers somewhere implicitly packed into their code. Now I would imagine that the game designers probably had those features really well internalized, so it made all sense to them, but for mere mortals this was impossible. So that's why the thing became extremely hard to control. So what they should have done is use this with a bit of weight decay or some other error penalty, and the algorithm would have been very nice, and I think they would have sold a lot more copies. So basically, if you use machine learning in reality, make sure you get it right. Otherwise there's great potential to screw up. Okay, so now we're going to do exactly what the question was before, namely, well, can we do some slightly different updates? And that's what we're going to look at now. So, in general, we'll have some empirical risk, right? And I can write that actually as an empirical average over this loss function. And so, the stochastic gradient descent update would be that I just randomly go and pick some x and y pair, and update my parameter vector here by, some step size, which may or may not be 1, probably it's going to be a lot less than 1, times now the gradient of my corresponding loss with respect to, well, okay, there's another type, there's an L missing here. The loss which depends on, the label that I observe, like, whether it's spam or ham, or, which language I'm dealing with, and here my score. And then in some cases you might want to make sure that your parameters don't actually diverge from a set, so you go and actually project them back in. And those projections, if you generalize them, would lead to prox operators, but we're not going to do much of that. What I'm going to show you, however, is that this algorithm, simple as it may be, for a suitable choice of ethers, will converge nicely. I'm not going to show you the worst case conversions, but just the conversion and expectation. Is everybody comfortable with this projection step? Okay, let me draw a picture. Let's say this is my convex set. And for the moment, let's assume that theta sits somewhere on the outside. Then the argument operation is going to find the x in that set that is closest to this. Quite often you use squared distance, but you could pick a different metric as well. And so actually the class of prox operator type algorithms like Vista will do that type of iterations of each step. Okay. Now let's look at convergence and expectation. So basically what we do is we look at the regret. So L star is basically the best thing you could do. And L bar is, theta bar is the parameter that we're going to estimate. And there's a theorem by Nesterov and Vial which show that the expected value of that regret is bounded by this expression. Now that looks a little bit messy, but we're actually going to plug in some numbers in the moment that make it look a lot nicer. Basically, this will mean that you will get rates like 1 over t, or in some case, log t rates. Okay, so L of theta is the expected loss, is what I'm getting. L star is the minimum of that. And this theta bar is just a weighted combination of past parameter vectors. So it's a little bit messy. So the point is I'm not just taking my last parameter vector, but I'm keeping essentially a weighted leaky average over all the past parameters around. It's probably a good exercise to think about how you can compute this cheaply, at the same cost as it is to actually update this theta t by just a simple gradient update. And essentially, the way how to do it is you basically expand the final sum, you get the weighted terms, and then it's actually fairly straightforward. But it's probably a good idea to think about it. So basically, in practice, never implemented as such. This is way too costly, at least whenever I have sparse gradients. And so for the proof, we're going to show that these parameters converge actually to the minimum. So I'm going to define RT to be the distance between, one of those minimizers, theta star, and theta t. So RT plus 1 is going to be, theta t minus the update, which I'm going to project. And I know that, theta t was within my set, within that set x, and theta star, which is less equal than the unprojected version. Because see, this was a minimum distance projection, I know that if this theta t plus 1, and maybe here's theta t, I know that after projection, this can only get closer, because it's a convex set. Okay. And then I just expand. That's what we have here. So we have the gradient, squared, learning rate, and then this is how far we are. Now by convexity, and actually there's another expectation that I will have to take with sums and so on, you can show, okay, so the first thing is I can just pull the RT on the left hand side. So RT plus 1 squared minus RT squared. That's basically improvement that I'm getting. It's less equal then, yes, well, this is upper bounded by the largest value of gradient you can see. And now I need to upper bound that last term. This is my current parameter vector minus the optimal one in a product with a gradient. Now by convexity, I can express that as basically the same term plugged in with the loss function. And then I can take the expectation of the loss functions. That's what gives me this. Now then, once I go and actually sum over all these terms here, this sum telescopes, because now RT appears once on the left and once on the right, and then I basically have my bound. So the cool thing is this gives me at least a randomized algorithm. In other words, I have an algorithm which in expectation is will behave. I might have to run it a few times until I find a good solution, but I know at least that if I run it often enough, I'll find something. And so now let's see what actually happens if we plug some things in. Because, if we know this R, the L, and number of terms that we have, we can just plug in a good value of eta. And since the order in which those etas are summed up doesn't matter, I might as well pick them all constant. And then by optimizing things, I can basically get something that's less than L times R over square root T. L was a bound on our gradient. R was the radius that basically how far we were from optimality initially. Basically that's the initial regret. And square root T is, T is the number of steps that I've taken. Okay. Now if we don't actually know T, so basically the algorithm keeps on running, at some point we're told, okay, stop now, then it's a good idea to pick this update rate to go like 1 over squared number of steps so far. In that case, you pay an additional log term, but otherwise the rate stays the same. So in practice, this is a much better idea. Now, if you have strong convexity, life gets even easier. Okay, question here?
So this convergence, right? How is it shown on the diagram? Is it somehow related on how you project it to the lines?
No, the projection is just something, basically the algorithm just, the theorem works regardless of whether you project or not. So in other words, if I have a constrained optimization problem, I can use this algorithm to get a good solution. Or I can have an unconstrained problem, in which case I just apply it right away as it is and I'm fine too. So So that projection step is just there because, you know, it in a way strengthens the entire result. It works even if you have to project. Other than that, it's exactly the same. Any other questions? By the way, thanks for asking. Yep.
To actually implement the projection, do you have to go through every single string and then find?
That very much depends on the projection operation. So it really depends on the convex set. So, simple example, suppose my convex set happened to be just a half space. In which case, well, this is trivial, right? I just, you know, compute the inner product with a normal and move accordingly. Another simple case is when I have a ball. So in that case, my set is this here, and it looks a bit more like an egg, but Easter is soon. And here's my parameter. And all I do is I just compute the length of this parameter and project it back. That's for an L2 ball. For an L1 ball, this is a little bit more tricky, right? So we have maybe that kind of object. Now if we are close, that's fine. If we are far away, then you know you want to find the closest point. And that will actually lead you to a vertex, which means that you're going to nuke a lot of non-zero parameters. And that actually gives you sparsity. So if you like a lot of, you know, sparse reconstruction results and so on, this is the type of applications that you want to look at.
But if you have 1,000 half spaces, you eventually have to go to it.
So for that type of problems here, you can use something that's called reverse water filling. So basically, suppose I have an L1 ball here with radius 1, then I just pick the first coordinate as the largest coordinate as it is. If that's less than 1, then I take the residual, I assign it to the second one, and you keep on distributing that until, you know, my unit length is gone. If I, so that's for instance an L1 projection. If I have a Q, I would basically, for each coordinate, you know, take the minimum between the value of the coordinate and 1 or minus 1 respectively. I would just clip everything. So it really depends on the convex set whether that projection operation is cheap or expensive. So there's a fair number of convex sets for which this is really expensive, but typically what you would hope is that that projection operation is something you can carry out very efficiently. And usually a clever trick on how to do this is what is in application papers where, you know, specific risk minimization problems of that form are being solved. They quite often have at its heart somewhere a very clever step for accelerating a non-obvious optimization subproblem. Then you put the general purpose, you know, optimization wrapper around it. You motivate the problem by writing one page of introduction of where it's applied to, and you submit it. Okay, this is maybe not a very flattering description of how some papers are written, but it's good engineering. Yeah, I know, this is all on the record. Okay, so strong convexity. Because let's see whether we can get through most of the optimization today. Yep.
Does the proof processor include a case for any projection, something like L1 or L2?
So, yes, any convex projection works. If you have a non-convex projection, you would be in trouble. So let me show you why a non-convex projection would be really problematic. And this is also one of the reasons why, in general, estimation with non-convex on non-convex domains can lead to really nasty convergence properties. Let's take something that looks maybe a bit like Pac-Man. It's a fairly fierce Pac-Man, but it's a non-convex set. Now, if I have a point here, right at the boundary, and depending on how I move it, I may project either here or there. And the gradients here and there may actually look very different. The net result is that I will get very big oscillations here, and I will have a horrible rate of convergence. This is exactly why non-convex projections can give you a lot of headaches. That said, if I have that domain, and I'm somewhere out here, then life's good. So you can actually develop a local theory of well-behavedness and show that things are, well-behaved in these situations. So the paper by Bob Williamson and John Baxter and a few other who proved this, I think they talk about what's called grout, the thing that you have between your tiles. And it's essentially how non-convex that object is that governs the convergence. So. And it's probably about 5 years ago that this paper was written.
How do you get like the upper bound to the gradient?
Pardon?
How do you get the upper bound to the gradient?
Okay, that's a very good question. How do I know upper bounds? Well, for most loss functions you have some information about that. So for instance, for the logistic loss, as we'll see, we have a nice upper bound that, that gradient is upper bounded by 1. So in some cases you need to know, what the argument, of your inner product is to get any further. So this is the part where you as an engineer or a scientist, when you model things, need to figure out, how you can bound things, whether you might use one or the other loss function, also in terms of its convergence properties. So all those things are fairly relevant. And so, for instance, something like the entropic loss may not necessarily be well behaved. And then you can either do some assumption engineering, and that's not usually so beautiful, or you have to use very different proof techniques. Or you just run it anyway and say, gee whiz, it worked, which is not very satisfying. Now, for strong convexity, so let me quickly show you what strong convexity is. Remember what we had before with the Newton method, where I said, well, if we can actually sandwich our function in between a, parabola above and below, then things converge nicely. And that's exactly what we're using here. So we have our standard Taylor expansion, and then I say, well, by the way, I can sandwich in another parabola below with this lambda. And then what I can do is I can use this again to bound the expected deviation. So RT plus 1 is this expression here. But now I have this additional strong convexity part. So it's actually missing here. It's a typo. It should be up here as well. The rest of the reasoning goes through as before. But now what we have is basically a difference that doesn't quite telescope anymore, because we have RT plus 1 squared, that's equal to RT squared minus this RK squared. So this gives us a slightly tighter bound. And at that point, I use slightly different averaging. So in this case, I basically use an exponential decaying averaging, and I do a little bit of algebra to get the convergence. So that's basically the entire trick. Now, you can actually do a lot better things than that. So for instance, you can adversarially prove things like this. So Ratliff, Bagnall, and Zinkovich actually show this order 1 over square root t learning rate. They get bound. And Charlie Schwartz, Cerebral, Singer, and Pegasus get an order 1 over t learning rate, and they get tighter bounds. Usually, those types of results look very, very impressive on paper. But they come usually with a condition that you need to know very well how well behaved your function is, what your modulus of strong convexity and so on is. Then these guys here, Bartlett, Racklin, and Hassan, actually exploit strong convexity to modify the estimation problem a little bit. And then there's a paper by Doe, Lee, and I forgot which other co-authors, which essentially optimize over this directly to get what's called conservative updates. This is probably one of the nicest stochastic gradient descent algorithms. Basically what it does is it starts off by saying, well, let's assume that my gradient is bounded in some way, or that my solution is contained in some ball. Let's run the algorithm. If we encounter the case that my hypothesis is violated, well, we just double all the constants and keep on running. And then if I've run the algorithm for long enough that within these constants it ought to have converged, I know I'm done. Otherwise, I just double and keep on doing this again. This is a very pretty algorithm. So you can actually parallelize and distribute that, and there's a couple of nice things to do. So if you think about online learning, well, we get an instance, we compute this instantaneous gradient, we update the parameter vector. Then the problem, of course, is that this is inherently sequential. After all, I've been telling you all the time, okay, how do we distribute algorithms? And I've been telling you for the past hour, or half an hour at least, all sequential algorithms. How do we actually parallelize this? And I mean, they are not even just machine sequential, but core sequential. And if you look at your disk, well, it's going to maybe give you 300 gigabytes an hour throughput, and it doesn't really scale to terabytes. So, and if I use a batch subgradient, then I need to compute maybe twice as many subgradients as I take update steps. So it's about 50 times slower. So can we actually parallelize things? There's a couple of ways how you can do it. One way is to use a data parallel approach, where each machine gets a subset of the data. I let it compute the loss and the gradient and update my parameters. Or a parameter parallel version, where I go and maybe take the first half of the alphabet and basically all the words that start with A. Let's say all the words that start with A from a text go into the first file, with B start go in the second file, and so on. And then each letter of the alphabet gets a separate machine. I compute parts of the gradients and parts of the scores. I aggregate terms and then update back. The problem is in processors, if I am data parallel and I have to do a round robin, I have a delay of n-1. Because basically, I cyclically compute my values and then I have to update the parameter again. There's no way really around that. If I'm parameter parallel, I can speed this up by a nice aggregation tree, but then I pay for the latency. But what it really amounts to is that I have that type of updates in both cases. So I compute some gradient, get some data, compute some gradient, have my learning rate, and then update, not with my current gradient, but with an old gradient. That's the commonality of all those algorithms. Now, if you think about it, really bad things could happen to you, because basically that delay could cause oscillations and things would diverge. So what you need to show is that things don't actually blow up and, are fairly well behaved. So, in terms of theoretic guarantees, for the worst case, you can show that if you have stochastic gradient descent with some delay tau on tau processors, then, well, it can't really be any better than sequential SGD. And, well, that is actually fairly easy to see, because if I have tau processors and I feed them all the same data, and I have to wait until I've seen all the data before I can actually take the next step, then, well, there's nothing I can really benefit from seeing the same instance tau times. I mean, I'm just telling myself tau times gee whiz, I wish I had updated my parameter, but then I have to wait tau steps until I can actually do something. If I have IID data, which is not adversarially ordered, I can actually do a lot better, especially if my objective function is smooth, and then I can get very nice guarantees. So basically, in the non-adversarial case, if tau is the number of machines, and this is, okay, so no, this is the adversarial guarantee. Basically, what I can see is that, my upper bound that we can derive, so this is another paper with Marty Sienkiewicz, Tom Langford, and I think Marcus Weimer, that basically is tau times t as an upper bound, and likewise for strong convexity, rather than what you would usually get, which is basically log t, you pay an additional tau factor. So this is basically, these are very disappointing results, but they match the lower bounds. Basically tells you, well, if I'm reordering the data as maliciously as I wanted to, well, I could screw you over. Now, the nice thing is that in the case where the problem is a bit better behaved and I'm seeing a random order of instances, then I'm basically only paying a constant offset, which depends on the delay. And then my rate afterwards doesn't really depend on the delay anymore. And likewise, I get something for strong convexity and dipshits continuous problems. Now, turns out you can even do better things than that. You can prove that for log-free updates where you just override parameters in a completely chaotic way, you can still get decent rates. Those decent rates are a little bit not so decent because they depend very strongly on the sparsity ratio of the parameters that I'm updating. So the birthday paradox will actually hurt you. So the applicability in these cases is a little bit constrained. But it basically means any reasonable algorithm will do well. Now, why is that actually the case? Well, if you think about it, if I'm doing stochastic gradient descent and I know my solution is over there, then initially if I hear 20 times move over there, well, I can't do more than just move there. So whether I hear that from one machine or n machines doesn't help me much. After I'm almost converged, my optimization is essentially a matter of averaging out the gradients to really squeeze out the last in terms of uncertainty. At this point, delay doesn't really matter very much because it's just an averaging process. So that's why I get a upfront cost, which is not so nice, and then a rate which is basically as good as the undelayed rate. Likewise here. So you can do all sorts of tricks. You can basically compute sparse gradients very easily. And the key trick if you want to do lazy updates for sparse vectors is that you really only need to look at the corresponding coordinate whenever that coordinate becomes non-zero in your gradient or also in your parameters. And you basically need to store a timestamp in this, and you'll get to figure out the details in the assignment. Okay, it works. Find multiple machines. So let me quickly show you something that's astonishingly simple. Basically, so far I've only shown you, how you can parallelize for multi-core, but not for multiple machines. And actually for MapReduce, this algorithm is insanely simple. It just performs stochastic gradient descent for each machine in parallel. In the end, you average the parameters. That's it. No need to really do much communication between them. I mean, it will improve and speed things up, yada, yada, yada. But it's basically one single MapReduce pass, and latency is not a big deal. It turns out that under certain conditions, you can get some not so easy to digest equation, which basically tells you you have a reasonable speed up from the number of machines. And I'm not going to go into details. It's a paper by Marty Sienkiewicz and Marcus Weimer, Lee Hong Lee, and I'm also one of the co-authors. It's all in the references section if you have the insane urge to go through a lot of math. But basically it tells you that this very simple procedure is easy. Now, let me show you something slightly sorry.
Could you clarify from the previous slide, right? What's the difference between a core and a machine? Like,
okay,
is it the processor and the memory pair?
Okay, very good question. So a machine is a physical box with a network connection. This machine has a communications bandwidth of about maybe 100 megabytes per second, and I need to actually perform a request to find out what that machine is doing. Whereas multi-core system is one which is sharing memory, where I have no latency to actually access the same, or I think negligible latency to access the same amount of data. So I can actually share all the parameters. But I may have to use all sorts of clever locking tricks because they might share a bus and do all sorts of other things. But basically, it takes me essentially no time to communicate between the various processes. So, for instance, this is a 2-core machine. If I were to take all of our laptops and put them onto one big fat rack, we'd probably get the 30 machine cluster. And the stochastic gradient descent that I just described would be one which, within each machine, just performs stochastic gradient descents on each core with some modicum of synchronization. And then it would aggregate those solutions from over-partitioned data in the end after everything is done. So this makes for a very simple algorithm. Okay. Thanks for asking. Any other questions? Okay. Good. So let's look at discrete problems. And these are actually quite nice ones. And this is very useful if you need to solve maybe some flow or transport problems. So think of the following integer program. So I want to minimize C transpose X, which is some cost, under the constraint that A times X is less equal than B, and that furthermore all the X's are actually integers, are integral vectors. So here I've drawn some lattice, and if my constraint set is in such a form that all the vertices are integral, I can relax from an integer to a linear program without any adverse effects. Well, there could be some adverse effects because I could essentially end up here on that facet, right? And then I would have to move to either one of those vertices to have an integral solution. And that can mess up relaxations in some cases, so you can get cases where problem at the same time can be relaxed as a linear program and is at the same time NP hard. Because it's basically those facets that can get you. Now, the trick is, of course, to identify when this is possible. And that allows for a very powerful family of algorithms. So in general, if you have a discrete optimization problem that looks sort of convex-ish, it's sometimes a good idea to relax it, solve it, and then to make the solution discrete again. And a lot of very good papers have been written about exactly that step, how you go from exact to relaxed to discrete again, and basically how much you lose. That's actually one of the more exciting areas of theoretical computer science. So, one example of that is when the matrix A is totally unimodular. So what that means is that my AX equals B has on its right-hand side B being an integral vector and A being a matrix for which every submatrix has as its inverse only integers. Now, why does that matter? Because basically in this case, my solution for the linear system, if only a subset of constraints is active, needs to, be an integral linear system. Because if it weren't the case, then of course my solution would never be integral. And it turns out that this gives me sufficient conditions for integrality. Now, of course, if I take my linear system of equations and divide it by, some arbitrary number, it stops being totally unimodular, except that, of course, the solution remains the same. So sometimes you need to cleverly reparameterize things. Can somebody see why this constraint matrix A must not have any entries larger than 1? Remember, we have this matrix. We want to make sure that any submatrix, let's say of those 2 rows and those 2 columns, its inverse is, you know, non-integral. What would happen if one of the entries were larger than 1?
Divide.
Well, I would divide by that, and I would get some number less than 1, correct? And that would destroy integrality. And so there's a couple of conditions, and total unimodularity is one of them. So here's a nice example. Hungarian marriage, basically the linear assignment problem. So the point is you have in Hungarian men, in Hungarian women, and they like each other with coefficients Cij. And so what you want to find is a permutation, pi permutation pi, which has exactly 1 non-zero per row and 1 non-zero per column, such that the score of the overall marriages here, so sum of pi ij, Cij, is maximized. Under the condition that those pi ij's are all integral, that I have only 1 per row and 1 per column. So in other words, this is a proper marriage, there is no polygamy, or vice versa. And the good thing is that this actually forms a linear constraint matrix, as you can see. So you can go in relaxed terms, and you get a linear program and you can solve it. It's not necessarily the fastest solver that you can use, but there are related problems to this where this is actually the right thing to do. So for instance, flow problems sometimes have this nice property as well. So parametric flow problems for, you know, resource allocations. For instance, if you want to allocate where web pages go on various caches, when you get that type of